Hi my dear students, welcome to my channel. Now the thing is number of tangents from a point on a circle. How many tangents can be drawn on a circle? So I am going to explain. There are three cases they have given in a textbook. So the first case what they have given. So here let us see. I am taken inside one point on the circle. There is a no tangent. Okay, there is a no tangent which is what is that, lying inside the circle. When I compare to that second figure, so what is this line? That is tangent. So which is at exactly on one point, okay, which is passing through that, so that we can call it as this is a tangent and point which is lying on the circle, right? So let us consider this figure. So the point which is outside, okay, so when it is outside, through that how many tangents we can draw? That is two tangents we can draw it, and PT1 and PT2 is called it as, so what is that, there are two tangents can be drawn and PT1 is always equal to PT2, that is we are call it as length of tangent from a point. Okay, so by using that, let us learn today the theorem 10.2. So it is a very important theorem. So definitely they will ask this question for 3 marks. So that let us learn what is that 10.2 theorem. Okay, so what is that theorem? It says that, let us read this theorem 10.2. So you should read the statement also. The lengths of a tangents drawn from any external point to a circle are equal. So what they have given here? They have given one circle. Okay, so they are given one circle. Okay, so there is a one circle. Okay, so here the point which is lying outside the circle, that point I take it as P. So when the point is lying outside the circle, through the point we can draw how many tangents? Two tangents we can draw it. Okay, that tangents, one I take it as Q and it is a point of contact, and one more is R. Okay, so they have given the length of tangent drawn from an external point, so PQ and PR. So those are the length of a tangent drawn from an external point P to a circle are equal. R equal means PQ is equal to PR, like that. So here you have to write given first. So our data given a circle with a center O. They have given a circle with a center O. Okay. So and a point P lying, you will write lying outside the circle, outside the circle. So here PQ circle, PQ and what is that, PR are the tangents from a point P, from a point P. So what do you want to prove it? You need to prove it, to prove. So what is that? Length of tangents are equal, so that PQ is equal to PR. So we have to write PQ is equal to PR. We have to prove it. Okay, so I do my construction now. What you have to construct here to prove that one? Only we are having a tangent and a point P. So that what I will do, I join OQ, OR and OP. Okay, when we join OQ. So give a name here OQ, OR and OP. Okay, so next proof. So proof and write it this one in a box. One we will write it as a statement and a reason. This is the way of writing a theorem. So you should write like this only. Okay. Okay. So here they have given, we need to prove it here. What is that? PQ is equal to PR, right? So that let us see the figure. Okay, OQ is perpendicular to QP. Okay, Q is a point of contact by using theorem. What is that? 10.1 theorem 10.1 we can say that. So tangent, what is that they have given? The tangent at any point of a circle is perpendicular to the radius through the point of contact. So here OQ is perpendicular to, what is that? Perpendicular to PQ, and OR is also perpendicular to P. And now we have got two triangles, right? So which are those two triangles? That is OQP, ORP. Okay. So what is OQ? OK is radius, OR is also radius. Yes or no? So here what we can say that here, so when it is OQ is equal to OR, we know that radius of the circle are equal, because this is a line segment which will join through the center to any point on the circle. So this is Q and R are the points on the circle. For that the line I have joined here. So these two are equal and one is right angle, and this OP is what? Common for both the triangle. Yes. So that let us write now. What is that? In triangle OQP and triangle ORP. Okay. So I write here OQ is equal to OR. Why reason we will write? Radius of the same circle. Radius of the same circle are equal. We know that. Okay. Now I write angle OQP is equal to angle. What we will write? Angle ORP. ORP is equal to 90 degree. Here I have used using theorem 10.1. Okay, what is OP? OP is equal to OP. So it is common for both the triangle, right? Common. So look at this. OQP is a right angle triangle. Okay, when we will take, so this is one side we have taken OQ, and OP is what? For angle which is opposite side is called hypotenuse, right? So even in this triangle also, OR is a radius, OP is a hypotenuse, and this is a 90 degree. So what is this? Therefore we can say that triangle OQP is congruent to triangle ORP. So we can write using RHS rule. or RHS theorem. We can write it using what is RHS? Right angle hypotenuse side. I have taken right angle. So this is the side and this one is a hypotenuse we have taken. So you can write a reason using RHS rule. Then once we have proved a congruent, we can write the corresponding part of the congruent triangles are equal. Yes. Which are the corresponding part? PQ is equal to PR. So I write PQ is equal to PR. That is, we can write it as CPCT. Once we have proved congruent, in that corresponding part are equal. Congruent triangles are equal. So this theorem hence proved. Hence